Our next speaker is Rahul Jayaraman. He's going to continue in our relativistic transient session.
Yes. Okay. Hello, everyone. I'm Rahul. I am a postdoc at Cornell, and I'm very excited to be the first contributed talk of the conference and talk to you all about what we've been doing with TESS, the Transiting Exoplanet Survey Satellite, and ZTF, the Zwicky Transient Facility, to study both the late and early time behavior of these sort of relativistic transients. So the first half of my talk will focus on a search that we've been doing for these late time flares in the LF bots that Anna mentioned. And the second half of my talk will focus on some new work that we're doing, searching and constraining supernova shock cooling using TESS light curves. And then I'll talk in a broader sense about how TESS fits into the overall landscape of these ground-based transient surveys. So luminous fast blue optical transients, these are events that are luminous, fast, and blue. They have magnitudes that peak between -22 and -20, if not brighter. They rise and fall over a few days to maybe a few weeks, as compared to the typical supernova timescales of a few weeks to maybe months. And these are blue. They have persistent color indices of less than 0. And so these events are observed across all wavelengths from X-rays to radio. And you can see here in this figure on the right that the X-ray luminosity of 2018 Cal, plotted in the teal right here, is roughly comparable to what we see for local university GRBs, which are plotted in orange. And so these observations at both X-rays at early times and radio at late times provides evidence for a central engine that pushes a shock into a dense medium. And this then powers the early emission of these transients. There's also further proof for central engines in these LF bots from late time observations of these events. The first is the observation of several episodes of late time flaring in these LF bots. So this is from Anna's 2023 paper on the Tasmanian Devil. You can see here that all these epochs marked with lines are occasions where there was evidence for flaring in 2022 TSD. And so the properties of the flaring, including the fact that it lasted up to 100 days, suggested that it occurred in a compact emitting region, had relativistic outflow velocities, and a high brightness temperature, implying that the emission source was likely non-thermal. In addition, very late-time observations of 2018 Cal have revealed a flattening of the light curve, kind of like a plateau phase, which suggests that there might be a stable accretion disk in the system. And so we have a JWST Cycle 5 program that was just accepted to probe the accretion disk SCD of the 2018 Cal late-time data. And so you saw this figure in Anna's talk, but basically I just wanted to highlight that, these flares rise and fall on really short timescales, that is of minutes, and they have really high luminosities. So it's very important that to search for these flares, we need a survey that has an observational cadence of minutes, that is able to observe and monitor the LF bot for a long duration after the initial emission phase, and has a bandpass that's sensitive to redder colors. And I'm sure you've all heard me evangelize about TESS before, but it's really good for this because it has a really large field of view of over 2,000 square degrees, and it has an imaging cadence of 200 seconds across its entire full frame. And you can see here, actually, it's sky coverage of the survey for the first 4 years of the mission, and we're actually in the 8th year of the mission right now, so that has helped us actually fill in this little weird top hat-shaped region that was missing earlier. TESS's bandpass spans the R, I, and Z bands, which means that it's very sensitive to these red phenomena, and which has made it quite useful, actually, in searches for an identification of gamma ray burst afterglows. Other surveys that could fit the bill for searching for these late-time LF bot flares include the Large Array Survey Telescope, which is led by Eran Ofek over at the Weizmann Institute of Science, and the Argus Array, which should be coming online in the next few years, which will have a field of view of 8,000 square degrees and a limiting magnitude of roughly 20.5 with a 60-second cadence. So you can see here how the 13 known LF bots compare to TESS observations of the location of the sky that they're in. You can see that we have observations from before the LF bot as well as after the LF bot. And I wanted to highlight that for 2024 QFM, we actually have TESS observations right at the time around which we expect it to flare, as observed in 2022 TSD. So that's actually a very interesting limit that we can place on flaring in 2024 QFM. This is an example of a TESS light curve for one of the LF bots at late times. surprisingly, there is actually not a detection of flaring. But I wanted to highlight that, one of the biggest systematics that we face in the TESS light curves is that there's a ton of scattered light at the end of each orbit. So each orbit lasts roughly 14 days. It's just the duration of this like yellow light curve, these yellow points in the light curve. And then as it reaches apogee, it really suffers from scattered light as the reflected light from the Earth and the Moon enter the sunshade. Often, we're also able to throw out sort of bad portions of the TESS light curves by observing a correlation between the light curve and the background, suggesting that any signal that we see is not real. And so folks over at MIT have recently been working on trying to model this complex scattered light background using generative AI tools, and I think they're working on the paper and publishing that very shortly. Here are some of the false positives that we actually had to deal with when we were looking for these flares using TESS data. So these are all solar system objects that are passing through the aperture of TESS. These have signatures that rise and fall on timescales of a few hours, and there's clear evidence of something that's actually moving through the aperture in the inspection of the raw difference images. So we know for a fact that these are not actually from the source, and they're just something that's sort of an interloper in the field of view. And so our main takeaway from this search was that there's no evidence for flaring in the TESS data at luminosities comparable to the original transient on timescales hundreds to thousands of days after the original event. And so we're currently working on actually making these qualitative limits more quantitative and putting exact numbers on the limits that we can place. And so looking forward, what sort of does the future hold for these flare searches? We calculate that flaring similar to 2022 TSD can be detected by TESS out to a redshift of 0.04. And if we don't care about resolving the sort of minutes duration substructure that we see here, we can actually bend the TESS light curve to timescales of 2 hours, which was roughly the duration of that flaring episode that we saw in the zoomed in light curve a few slides ago. And we can detect these flares, or at least evidence for such flaring, out to hundreds of megaparsecs. In addition, we have more optimistic predictions from other large surveys, such as LAST and the Argus array, and we may even be able to get a few tens of detections with the Argus array of flaring at late times from these events. But of course, given that the rate of these LF bots is so uncertain, that's why these rate estimates are also quite uncertain. So it should be taken with a grain of salt. So now I wanted to shift gears a little bit and talk about some of the stuff that we're doing for early time light curves using TESS, particularly with the focus on supernova shock cooling. So TESS's cadence and continuous monitoring helps us search for and constrain shock cooling emission in core collapse supernovae. So you can see here an example of a really nice shock cooling light curve from TESS in SN 2021 ZBY. You see here the well-resolved early shock cooling peak, followed by the typical radioactivity-powered supernova peak and decay. Another particularly interesting event was 2023 AEW, which exhibited a transition from type 2b to a 1c. And you can see here actually that TESS was the only survey that was able to catch this first peak, this first rise and fall, and then a lot of other surveys and follow-up observations caught the second peak. And so the prevailing theory for 2023 AEW, some folks thought that this might have been an early shock cooling peak, but the timescales didn't really make sense. So now people argue that this actually early peak was likely the radioactive powered supernova, followed by some maybe delayed interaction with a circumstellar medium. And so we used the ZTF Bright Transient Survey and cross-matched it with TESS observations to see whether or not we would be able to find any evidence for shock cooling in the TESS light curves and help constrain the progenitor radius. And unfortunately, we didn't find anything. But what we're hoping to do is combine TESS with Rubin and ZTF to search for this early shock cooling and other interesting flux features at early times. And so this is also very interesting because for these central engine powered relativistic transients, we might be able to probe pre-explosion mass loss with this sort of high cadence, well-resolved early time light curves. And you can see here actually sort of a simulated LSST observation of a type 1C BL that was observed by TESS. You can see here that TESS has a really nicely sampled light curve across the first 20 to 30 days of the supernova. ZTF provides color information, and then LSST, unfortunately, with its 4-day cadence, may not help us constrain the shock cooling emission, but it will help us monitor these transients out to late times. And so each of these three surveys brings a unique advantage to the sort of search for fast transients and other phenomena. TESS provides high cadence light curves and frequently revisits fields roughly every year to 2 years, which enables searches and constraints on late time flaring in these events. Additionally, ZTF provides early time color information through its ongoing GRI band follow-up, or GRI band observations, rather, of the field that overlaps with the Rubin field. In addition, with the Lion survey, which is being led by Kay Ryan, we're also hoping to get spectroscopic classifications of these bright transients that lie in the LSST ZTF overlap. And of course, Rubin will be a discovery engine for all of these transients. As I'm sure you've all heard, we'll get over 1 million alerts per night from Rubin. And so it's important that we actually develop and fine tune our filters so we can catch these fast relativistic transients in the act. And so here, I also wanted to highlight another potential use case for TESS and Rubin. This is for a GRB afterglow from 2020. TESS was able to find evidence for prompt optical emission in this GRB afterglow, as well as a flare in the afterglow. And then Rubin would be able to monitor it out to really late times with its 4-day cadence, even if it's in different band passes. And so with that, I would like to conclude by saying that we searched for late time flaring in LF bots using TESS and didn't find anything, and we're working on quantifying the limits that we've obtained. We searched for shock cooling emission from core collapse supernovae in the ZTF bright transient survey and didn't find anything, but we're working on hopefully being able to constrain the progenitor radii of these systems. And so in the future, what I'm hoping to do is, as part of this, to compare the different TESS difference imaging algorithms that are out there, because one issue that we've been facing is sort of flux calibration with the TESS light curves is kind of difficult at times. And so if we have a robust comparison of all the tools that are out there, it'll be really useful to figure out sort of what TESS is observing and how we can characterize it. In addition, I'm working with Ruslan Kono over at Weitzman on flare searches in other transients, such as TDEs and supernovae. And finally, I'm hoping to fine-tune the fast transient filters that we have for ZTF and LSST and integrate them with the TESS difference imaging photometry so that we can get like rapid constraints on any possible precursor emission, late time emission, or even like early time shock cooling emission. And with that, thank you so much, and I'm happy to take any questions.
All right, thanks Rahul for the nice talk. Questions for Rahul? Let's see, let's go to Oz.
This is a really interesting talk. I'm wondering if you can talk a little bit about how you plan to use Rubin for something like shock breakout, where maybe you're only going to have a point every 2 to 4 days. Is it purely discovery? Have you thought about like how do you identify something that you really think is a shock breakout signal?
Yeah.
Shock cooling signal, yes.
Yeah, that's a good question. So Rubin is mostly, at least in the framework that I envision for TESS, like going to be a discovery engine. And so the TESS like downlink cadence is unfortunately once every week. And so that sort of introduces a latency in what analysis we can do, what rapid follow-up we can do. But if we get that TESS data and we see that there's a shock breakout or a shock cooling event, then we can add that to the models and that can inform further follow-up.
This might be not the main science you're interested, but those interesting flares in TESS, which didn't turn out to be flares at all, but instrumental effects. Could you tell a little bit more about them? Like, do you have some?
Yes, these, right? So these are actually not instrumental effects. These are asteroids, or sorry, these are solar system objects passing through the field of view. And so what we did is we just did a cone search in the Skybody tracker for any potential rocks that were passing through the field of view and figured out which ones could be the likely candidates based on cross-matching the magnitudes and the time and the location. So, yeah.
Hi, wonderful talk. Thank you so much. So the flux that you get, are you using the SAP flux from TESS when you do this? And then you are correcting for instrumental effects yourself, or do you use the PDC, or what do you do to correct for these effects that you're seeing?
Yeah, so what we do with TESS, so I use Microfosnaw's difference imaging pipeline, which is built on top of ISIS. And so to do that, we like self-consistently calculate the flux and estimate that using like the sort of what's called the out of transient portion of the light curve, like a flat portion of the light curve. So we scale
Got
it
it.
based on that, we self-consistently based on the RMS of that out of transient scatter.
Wonderful. Thank you very much.
All right, thanks for the great questions. Let's thank Rahul again.